Well, I want to thank David for his introduction. This is an amazing meeting. Such inventive people. I've really enjoyed the morning. It's been great. I am going to talk about Kinect that David mentioned, but before we get to there, I want to sort of work up to it and tell you about one or two other things. So, I've worked for about 30 years in computer vision. You know, I used to be an academic, and then I moved to Microsoft 12 years ago. And computer vision, that is making machines that can actually see, that can understand the input that comes to them through a TV camera, is an incredibly difficult thing. And so the academics have been thinking about this for, it's about 45 years now. And I just want to say three things in the course of this talk. First of all, just briefly to convince you, if you aren't already susceptible to this idea, that vision is going to be something very hard to get a computer to do. Second idea is that vision necessarily is about probabilities. And this is a slightly curious idea because we think of computers as being machines that compute with numbers. And you know, we think about them doing sort of financial stuff easily and crunching data easily, and that's all kind of numerical. And you put stuff in, and the handle cranks, and you expect to get some numbers out. But perception, vision, and other forms of perception that humans do and that animals do somehow transcends that very mechanistic way of thinking that you just put some inputs in and turn the handle and get the outputs. There's something much more subtle going on, and that's one of the ideas I want to leave with you. And the last idea is that, you know, I think something to celebrate, because I've been in this field for such a long time, is that now vision really works and is a technology that people can use to make stuff and to do things commercially. And that's, you know, only a change that's really happened in the last 10 years, and Kinect is one part of that. So I dug out some of the archives. A report, I don't know if you can actually read this, from MIT. This is just a little bit of a proposal that Seymour Papert, who was one of the pioneers of artificial intelligence, made back in '66 to think about solving vision. And they were thinking about artificial intelligence generally and how you solve the problems of artificial intelligence, and they thought vision would just be a kind of a small corollary of that. You know, while we're doing reasoning, we might as well reason about a few images. And so they set a summer project for a student, and the basic stuff, seeing simple objects, balls, cylinders, blocks, that was supposed to be done in July. And once they'd licked that, they were going to go on in August to slightly more complex objects, you know, not quite so geometric and so on. So, you know, they thought a couple of months should see them through. Well, you know, 40 years later, we were still trying to solve this problem. And it turned out they'd been perhaps a tad optimistic. Why is vision hard? Well, here's one way of thinking about it. Supposing you want to build a machine that will recognize and understand that there's a hand in the middle of that scene, and you know what configuration the hand is in, and so on. It sort of seems effortless to us. We've got this massive computing apparatus. The apparatus for vision all around the back is a very large proportion of what's up there in your head, and so we are so good at this that it seems it deceives us into thinking that the job is simple. So you might think that you could write a program that would take the image in the middle and produce the outline on the right pretty simply. But an interesting thing happens when you treat the image as a signal, rather like in the earlier talk we saw sound portrayed on the screen as a signal. There was a graph. So you can think of images also as a signal with patterns of light and dark, you know, portrayed with your favorite visualization tool. And you'd think if you took that signal and you passed it through some signal processing machinery or code, that somehow you could pick out the outline of the hand. After all, the outline of the hand seems to be a transition between lighter stuff and darker stuff. You'd think there would be a way that you could express that sort of mathematically and capture it and get it all coming out. But when you do that, when you try those kinds of techniques, what you get is the kind of scrambled egg on the left. And there's a whole lot going on in there. Actually, the contours of the outline of the hand that you want are there, but they're also mixed in with a whole lot of other stuff, shadows and bits of texture on the hand, and stuff which as humans we just effortlessly filter out. We don't even realize we're doing it. But for the computer, the computer, a bit like the geek that likes the ballroom dancing, they take things very literally. And when the computer looks at the image and takes it literally, that is what it gets, what comes out. The thing on the left doesn't get you very far with trying to interpret what's in the scene. Now, actually, the previous picture with all that texture in was beginning to look a little bit random. What the computer sees, the image that we had on the left there, there's a lot of texture, there's a lot of randomness, random pattern. And this is really a feature of vision. So here's some more scrambled egg that I put on the screen. And I wonder how many of you are actually seeing anything rather than scrambled egg. Put your hands up if you can sort of see something coherent. And put your hands up if it looks like just a mess of scrambled egg. So you see some people have managed to perceive something and others haven't. I promise you there is something there. There is something coherent, something so obvious that once you've seen it, you'll kind of kick yourself and wonder why you didn't see it before. And what's more, you won't be able to unsee it. Once your brain has organized that signal and you've seen it. And by the way, a clue is it isn't a Dalmatian dog. This demo is more normally done in the psychology textbooks of the Dalmatian dog. I thought I'd bring something different this time. Anybody, sort of while I've been talking, seen something that didn't see it before? Any perceptions? Yes, thank you. One or two people. There's a face in that scene. See if that helps anybody. So towards the top, there's a face. There's a couple of blobs at the top there, which are the eyes. I don't know if I've got the... Yeah, here we are. There's an eye. There's another eye. A sort of a lot of beard. This is a very beardy guy, a kind of evangelist or something. I've got a smaller one of him. You might find it easier to see him in the smaller one. But the point I want to make is that there's a lot of random signal here which is being organized in a highly opportunistic way by your brain, kind of forming hypotheses. It's not at all a sausage machine, what your brain does. We don't just put this signal into your brain and turn the crank and the answer comes out. It's much more like your brain is rushing all over that signal, forming hypotheses. Could this be an eye? If that were an eye, then this thing next to it would be more likely to be an eye because eyes occur probably together and so on. So the point I'm trying to make is that what's going on here is fundamentally probabilistic. That's what goes on in the human brain, and that's what we had better emulate if we want to succeed. Here are one or two, three, in fact, famous scientists that I've dug quotes out for. Richard Gregory, very well-known psychologist, died recently, worked at Bristol all his life, and his view was that perception, what humans do, is all about forming hypotheses in the world. You're never certain. You're all the time lifting hypotheses up to the data, testing the hypotheses up to the data to see if it's supported or if it's not. It's all about testing evidence and forming hypotheses. It's like our brains are kind of professional statisticians rushing around in there trying to make sense of the data in the world. Here's Horace Barlow, physiologist in Cambridge, and so he's looking at things from a rather different point of view, thinking about cells rather than psychology. But he has essentially the same view, that perception is all about making sense of randomness, all about forming hypotheses and doing things with probabilities. And finally, David Mumford, the Fields Medal winning mathematician, who turned from mathematics to trying to understand the brain, and also after a decade or so of studying the problem, came to the view that, yes, it's all about computing with probabilities. So we should expect that the computers we use to solve this vision problem are not going to be doing arithmetic like we think of computers doing. They're going to be doing something rather different, computing with probabilities. Here's a snapshot of a computer about 15 years ago trying to compute with probabilities. So it's looking at a scene, it's looking for heads, and it's scoring many different locations in the scene according to how probable they are to be heads. And this is somewhat, being 15 years ago, this was a little bit primitive. The computer had a not very highly tuned idea of what a head was, so actually bright red is its strongest hypothesis, and that one looks quite good. Some of the green and yellows are not too bad. The whites are a bit crazy. It thinks that book up on the shelf there could possibly be a head just because it's not a very sophisticated computer. But the interesting thing about this is that this was one of the first programs that actually reasoned in this way, rushing about the scene, forming hypotheses, looking for evidence, and treating the whole world as if it was a giant experiment. And here is, this depicts a computer. This is commonplace now, learning how to see faces. And you see the computer has correctly labeled all the faces in the scene. And it's very hard to tell a computer what a face is. If you tried to write down a set of rules, the kinds of rules that a programmer might put into their program about what is a face, it's very difficult to capture it. People have tried very hard, and it just doesn't work. What does work is to show the computer a whole lot of faces, like the ones on the left there, and then you also have to show the computer a whole lot of things that aren't faces. Of course, they're not in short supply. There are plenty of those around, but that's what you have to do. And the computer gets to try to generalize about what it is that makes up a face, and it does this also in a probabilistic way. Okay, so vision is hard. Vision is essentially probabilistic. And the last thing I want to tell you is that vision works. And I'm going to kind of go quite quickly through this, but people have got Oscars and Emmys for computer vision technology, which is now commonplace in the movie industry. And for example, the stuff that makes the candles float in Harry Potter, believe it or not, came from vision. And what about face detection in cameras? You probably all have cameras that know how to group shots. It's using pretty much the technology I was illustrating a couple of slides back. It's become commonplace, and this is something that you can really sell commercially. Here's an interesting example, because this is a small company making a business out of computer vision. This is a system that detects people who've sunk suspiciously in a swimming pool and alerts the guard, and they go and rescue the guy. Computational photography is another thing which you probably don't realize that there's computer vision going on under the hood, but nowadays when you stitch panoramas out of your photographs, you don't, like you used to, have to take the photographs very systematically, kind of raster scanning the world. You can do them in pretty much any order, and the computer will make sense of that like solving a jigsaw puzzle. And that's essentially what a fallout from work in artificial intelligence, trying to understand the structure of images, that these jigsaws can be solved automatically. And that picture there is a very wide angle, and of course it's not really a single photo. It's put together in that way. Something even more amazing, it's like a three-dimensional panorama. I don't know if you've seen this photosynth. Some of my colleagues in the lab in Seattle made this together with the university there. And it actually does that same kind of panorama stitch, but it can do it with everybody's photographs. So if 100 different people have all photographed a scene, let's say the Pantheon in Rome, somehow the system understands how to put all those together, not just in 2 dimensions, but in 3 dimensions, so that you can actually walk through and flip seamlessly from one photograph to another. It's as if you were walking around the three-dimensional object. Something we did in our lab, again, some fallout from some more ambitious work in computer vision. What we were trying to do was to teach a computer how to separate an object from the background in a kind of general setting that could be used in a recognition program. In the general setting, it turns out to be pretty difficult. We're still beating on that general problem. But then if you bring that down to a kind of interactive setting, what you would do with PowerPoint or with Word, it turns out you can easily make a tool which it will extract an object like that turtle at the top left, take it away from its background, and put it into the scene. It is pretty much a one-click thing, and it's effortless, and it's sort of deceptively effortless, but actually what's going on under the hood is a lot of probability computing. Okay, so now to get to Connect, which David mentioned before. Connect is a new kind of a camera. You see it at the top right there. It's got several apertures. It's actually a three-dimensional camera. It perceives the world in depth a little bit like human vision using the 2 eyes, but replace one of the eyes with a projector and spray the light out instead of sucking the light in. So the light comes out of one eye, as it were, and gets sucked in the other eye, but still the same three-dimensional principles pertain. And this has allowed us to build and commercialize the system that David mentioned, which is a new generation, I would say, in gaming, because now you don't need to be a hardcore gamer to enjoy gaming. I'm the living proof of that. I'm an absolutely useless hardcore gamer, but these things are fun. It'll even teach the geeks to dance. So something called Dance Central, and you try to follow the guy who's teaching you what to do, and your limbs glow red hot if they're in the wrong place, and you know that was wrong, and you don't get a very good score. You do it again. And by the time you've done 3 hours, you're going to be full of confidence at the disco. So as well as being something for gaming, I think this is something quite new also for user interface. So You know, we used to have, years ago, green screen and cursor, then we had mouse and windows, then we had touch and multi-touch more recently, and what we've got now is essentially no touch. The three-dimensional camera just perceives the human body, and this is available for use as a very flexible interface. Now, I think this is very early days, and nobody really knows how to use this device. We've worked out how to use it for gaming, but the implications are much broader. I think this could be part of a new way of more effortless communicating with all kinds of devices and machines, including machines that we don't think of as having anything to do with computing, like, for example, your car. Here are some of the applications one might consider. At the bottom right, you see a head-up display in a car. These are becoming more common. And when you see information in front of you in the car, also very natural to want to point at it to pick things out. Many other applications. Medicine at the top in the middle. People in operating theaters don't want to use a computer while they're in the middle of an operation. But if they could gesture and maybe combine that with voice, that would be a whole new level of flexibility. It's a hard problem, though. The problem we had to solve that David mentioned of understanding what the human body is doing when presented in 3 dimensions to a camera. Why is it hard? Well, humans can do very many different things. Look at the picture there, just to remind you of all the weird shapes we can put ourselves into. We come in many different shapes and sizes, let's be honest about this. And all of those have to be encompassed, well, shapes and sizes. And with accessories. Many of us come with accessories, and that makes us more difficult to, half of us come with accessories. That makes us hard to perceive. We can be camouflaged. This is where, of course, the depth camera is fantastically powerful, because you may be camouflaged with respect to texture, but still stand out in depth. And you can be in very complex situations with other people and so on. To cut a long story short about how we solve the problem, we were doing some wholly speculative work on artificial intelligence and trying to understand how we could get a computer reliably to label maybe 20 different kinds of objects in scenes. We were doing this work 4 or 5 years ago. Some of us thought even it was a little bit crazy to do this. It's just too speculative. Why would anybody want to do this? What would you do with it when you'd done it? Anyway, we were kind of fascinated, so we worked on it. And it turned out that as I say, to cut a very long story short, because people have attempted to solve this problem, perceiving the human body in many different ways and failed, but it turned out that treating the human body as an object to be recognized, or more accurately, a cluster of objects, so the upper arm is an object and the lower arm is an object and so on, was the critical thing. And here is the training data we used, over 1 million different examples of people of different shapes and sizes doing different things. And that training data was fed into programs which I wish I had time to tell you how they work, because it really is a fascinating story. But just the key thing is, again, learning how to do the task, just like with the face recognition, using probabilities to compute, because these perception tasks are essentially probabilistic. That was the key to solving it. And so now that ability to label parts is embedded in a pipeline. You see the second panel in the pipeline there is the output of the labeling. The and fourth are further processors which finally get you down to the joints of the body, so that we can track now in real time at the same rate as the camera is running, 30 frames a second, the joints of the body. And that is a very flexible and general input device. Here you see what it does from several viewpoints. Now, we released that capability out into the developer world, and people have been doing amazing things with it. And I want to finish by just showing you one of the things that we have done most recently in the lab with the 3D camera. I guess it's not exactly what it was intended for, and this is what happens when people play with new inventions. And in order to show you exactly what this does, I have the help of my lovely assistant here, David, who is going to come, and I think we need to put you sort of in range of because you don't have a wireless version yet.
Am I going to wear rabbits?
It's not going to hurt, David. Just relax. Good. And now Otmar Hilliges, who is one of the team who worked on this, is going to scan David, and let's see what happens on the screen. The point is the camera itself is not a very high-resolution device. It doesn't need very high resolution to do its job in perceiving the human body. But once you start to move the camera around, of course, it's not just one depth image of David that we've got, but we've now got dozens and dozens of them. And so the new facility, which we call Kinect Fusion, is taking all of those low-resolution images of David and composing one high-resolution three-dimensional image. So now we've got something which we could send off to a printing facility and have a bronze David back. I think we should have you probably out in the lobby by the end of the day, gorgeously carved in bronze. This is something which you could do before. Actually, you could buy a device to do this, but it would cost you many tens of thousands of dollars. The Kinect camera is $150, and now essentially what we've made is something that anybody can use for carving out high-quality three-dimensional objects, just without any specialist help. Thanks very much. Thanks, Otmar. Thanks, David.
Thank you.